Thank you, Ishan. Thank you for the welcome, and thank you all for joining in this webinar. So, before we get into all the technical details and all the nitty-gritties of what is industrial control system, let me go through what our organization provides in this field of service. So, first, our organization is a certain panel globally recognized award-winning organization. Since Jan 2018, we are working with many kinds of organization in the field of IT security, with government organization, power plants, manufacturing, logistics. We're also providing them compliance facilities like a gap assessment based on ISO 27001, 9001. We're also we're also conducting security assessment on plants. So these are some of our cybersecurity services: OT risk and vulnerability management, OT compliance gap analysis, secure OT architecture consulting, OT SOC and threat detection advisory, OT incident response readiness, secure product development consulting, supply chain risk consulting, OT security and awareness workshops. So these are some of our services, and we also have our in-house solution, SRC OT Shield X. So this is basically a intelligent, smart OT assets and vulnerability management platform. So we have several features such as asset discovery, identification, protocol-based scanning, vulnerability scanning, network mapping. It is a quick setup, plug and play device, a non-agentic approach, and there are multiple options and multiple features that you can use to safeguard and get a visibility of your OT environment. So now, without further ado, let's get into the main topic of this webinar for which all of you are waiting. So these are some of the components that we'll be covering in today's webinar. What is ICS? What does it mean? What are the unique challenges in the ICS? The key components of the ICS, threats, risks, what are the best practices, and what is it that we can do for you? So first, the major question here comes: what is ICS? So ICS is a term that means industrial control system. It is a broad term for the complex systems and components used to control and automate physical processes. If I will give you a real life example, let's take the example of a wind turbine. A wind turbine is rotating, but how much energy it is generating? All these calculations and all the controls of the physical turbine is done through the ICS system. So now let me highlight the overview of the components of the ICS system, and later in this session we can deep dive into them. So the first component is SCADA. SCADA means supervisory control and data acquisition. It helps us visualize and control all the assets that are present in the different geographical location in the field. Then we have DCS, distributed control system, which manages complex interconnected process. And then we have PLCs, programmable logic controller, and that executes automated tasks at a device level. There are many more systems and a vast architecture, but for now, we can continue with these. So now, where is ICS used? Okay, we know it is industrial control system, but where it is used? So we have electric grids, water facilities, manufacturing, transport systems, and pharma and chemical industry. So as you have already known that these are some things that need to work 24/7 to ensure that our daily lives are not impacted. For example, the electric grid generates power 24/7, and that is why we are going to attend this webinar also. So now let's see how this infrastructure works, what are the insights of the infrastructure, and later we'll move on to the security part. So the next is ICS security versus traditional IT security. So now you will all say, okay, it is computer which is showing some data. Why do we need a different security mechanism, different security framework to protect these things? So before understanding that, we have to understand what is the role of these systems. When we come to IT systems, which focus majorly on preventing unauthorized data access, data integrity focuses on digital assets, database, and internal communication, whereas ICS prioritizes on safe and correct operation of machinery, data accuracy, and preventing unsafe equipment behavior. When it comes to the life cycle of an ICS environment versus the IT environment, the IT environment undergoes frequent updates, patching, and changes. For example, every 15 days you get a security update, you get a new OS update. You can install, uninstall applications as you want. You can put in new applications today, and in the next moment, you can move them out of your system. But this is not the case for an ICS environment. An ICS environment run for decades without any changes or a minimal change. There are no to minimal maintenance windows, and they often use proprietary and legacy hardware and software. For example, a plant that was set up in 2008 and it is still running and generating electricity and has not been out of commission for even a single day cannot stop its systems for 2 3 hours to just update the Windows version. So these is the whole overview of ICS versus IT security. So now, after I've explained you these concepts, I believe you are now getting the idea why are we in the need of specialized ICS security. So these are the major points that we are going to see in this presentation. Legacy system. What is a legacy system? Legacy system is a system that is declared end of life, and the company has said that we are not supporting any kind of security patches for the system. To give you an example, let's take Windows 7. Windows 7 was a very good operating system back in the day, but now Windows 7 is a legacy system. It no longer receives any kind of system updates. It no longer has security patches being delivered. And Microsoft has clearly stated that this is end of life. But when we look at the older ICS infrastructures, such as power plants or oil rigs or manufacturing plants, they may still be running Windows 7. So they have legacy systems. Real-time constraints. When it comes to controlling physical devices, on-field devices, and it also involves high stakes such as human safety and environmental impact, real-time decision making plays a crucial role. We cannot put in any kind of device that will impact the network and cause a delay in the commands or the decision making in the environment. Because if there is a delay in decision making in the environments, there may be some incident related to loss of human life or any kind of environmental impact. Air gaps. What is an air gap? So this is a new term that has come into this presentation. Let me give you a short description what is it, and later we can deep dive into the air gaps. So basically, air gap is a segmented network inside the ICS environment to protect the environment from being accessed from outside. It is done to ensure that the systems can only be accessed internally and no external adversary can access the system. But in the case of newly developed architecture, we can construct secure remote access through IPsec tunnels, VPN tunnels, using which we can securely access the internal network. But when we say this about the older plants, this this cannot be accessed because there are legacy systems which are vulnerable to newer security threats. Now let's move on to understand the ICS infrastructure in depth. So let's first understand the key components of ICS. So first, there are field devices, sensors and actuators. Sensors monitor the physical parameters such as temperature, pressure, flow rate, voltage, and current. They translate the real-world physical signals into electrical data and sent to controllers. So basically, how much energy is generated, it is transferred from a solar panel to the computer. Actuators execute commands from controllers to effect changes in a physical process. When I say this, let's imagine there is a fan running and we have to stop it using a computer. So that's what actuators do. It involves, for example, valves, relays, motors, and pumps, which and adjust the system according to the controlled instructions. Then we can move on to the controllers, programmable logic controllers, and distributed control systems. Programmable logic controllers are designed for real-time deterministic control. They gather data from sensors, process logic, and output signals to actuators. PLCs, which we can also refer to them as, are scalable, highly reliable, and used for machine-level tasks for entire plants. Distributed control system, which is used for continuous monitoring, complex processes. They decentralize functions over multiple controllers and field devices, but provide centralized visualization and management. DCS also includes advanced process controls and sequence management to ensure fault tolerance. Remote terminal units or RTUs. These are small devices, microprocessors, for interfacing with field equipment in geographically dispersed locations. So for example, let's take the example of a solar plant. So the solar panel is scattered all around the field. So are the generators, UPS, batteries. So they are all connected and controlled by these remote terminal units. RTUs collect data from sensors and communicate with the supervisory system and support remote control and monitoring. Supervisory system. So now we have moved to the systems that control all these devices. So for that, we have SCADA system. SCADA aggregates data from PLCs, RTUs, and other devices, providing real-time visualization and historical trending. Operators use SCADA to supervise processes and respond to alarms. So basically, if you imagine an infrastructure, in the control room, there are people monitoring the devices using the SCADA. They can turn the devices on off, they can monitor their state, such as example temperature, how much memory it is using, or are there any fault alarms, for example, are they overheating. So all this monitoring is done through SCADA. So now let's move on to the typical ICS architecture. So now this architecture is based on the frameworks or the standards. In different kind of scenarios, the architecture may differ, but this is according to the security best practices. So, sorry. So first, we have the enterprise layer. What is the enterprise layer? So it's basically where the decision making related to the plant is done. So this is the IT network where people are sitting, doing meetings, and taking decision about the plants, answering to emails. And for keeping it simple, you can call it the office or a headquarters of the plant. Then we can move down to the supervisory layer where the SCADA and DCS system lies. So here, all the data from the ICS network comes. And between the enterprise and supervisory layer, there is a DMZ, demilitarized zone, or a firewall. So the enterprise layer and the supervised layer are protected with a firewall. The enterprise layer cannot communicate with the supervisory layer, and here comes the network segregation part. The supervisory layer contains SCADA system. So the SCADA system, here people are monitoring the whole plant and controlling the field devices, the RTUs, the PLCs, as I've told you before. After that, there is a control layer which has HMI. HMI is human machine interface. It provides a visualization of a machine. So basically, how much processes is it using? What is the temperature currently? What function it is running? So engineering workstation and control servers. To control the field layer, the sensors, the actuators, the PLC, the control layer provides a crucial importance. The people here are responsible for ensuring that the sensors, actuators are running. Also ensuring that the proper commands in real time without any error are transported to these field devices to ensure that the architecture is run. I'm saying again, this architecture is based on security best practices. Real world architecture may differ as per the environment. So now we have learned about what were the architecture. We have learned about different components. Now let's see how is this vulnerable to different kind of threats. So what can be different threat actors in these devices? First, we have malware. So on the presentation, you can see the names like Stuxnet, Triton, Flag Energy. So these are some highly renowned real-world malware cases that has happened in the past decade. Stuxnet was a highly sophisticated worm that targeted PLCs and SCADA systems to physically sabotage centrifuges while reporting normal readings to operators. So it basically showed different readings on the PLCs and different to operators. So that means the operators in the control rail will not know what are happening to my PLC devices. Then they have unauthorized access. So basically, the major role is the default credentials and default configuration. SCADA systems or the ICS infrastructure often work upon the default credentials. Default credentials allows an attacker to easily gain access to this system. And by the exploitation of these weak credentials and the password, the attacker can instantly gain access to the environment and cause disruptions. Misconfigurations. What are misconfigurations? Installing a firewall and enabling network settings are not enough. Those are to be regularly checked as per the security best practices. Misconfigurations allow an attacker to bypass these firewalls and network settings to reach the critical field systems and causing disruptions. The firewalls and the network settings are to be configured properly so that proper network segmentations can be done. Without proper network segmentation, an ICS environment is vulnerable to different kinds of threats. Insider threats. This is a common threat in IT infrastructure also. But when I come to ICS, insider threats, may it be planned or unplanned or a mistake by a simple plant operator, can often give an adversary access to the plant. Employees, trusted partners, or contractors may intentionally or unintentionally compromise the ICS security, especially if access controls and monitorings are inadequate. Privilege misuse, sabotage, or careless behavior can enable external attacks or cause disruptions. Unpatched vulnerabilities. As I told you before, several plants are running on legacy system. The plants cannot be stopped for updating the softwares. So there has to be some vulnerabilities that are unpatched. As the time passes by and there is no updates, the systems become vulnerable to modern security threats. There, attacks such as supply chain attacks, exploiting software flaws, a open source script, or a malware can attack your plant. An adversary can launch targeted attacks against the unpatched vulnerabilities to gain instant access to your ICS infrastructure. So till now, I'm guessing that you have understand what are we trying to say. We are saying availability is important. We by any means the plant should be running, the infrastructure should be running. Now let's look at some real world attacks on ICS. So here in the past decades, I have collected the information about some attacks that has shocked the world and ring the bell that we need ICS security. Stuxnet 2010 targeted Iranian nuclear centrifuges. A highly sophisticated worm spread via infected USB drives. So basically, someone plugged in a drive and it all went down, which targeted Siemens PLCs. A Siemens is a highly renowned manufacturer in this field of ICS. So, what was the impact? The secretly manipulated centrifuge speeds to cause physical degradation and failure, while hiding the sabotage from a plant operator through manipulated HMI readouts. So basically, the field device that was the centrifuge was affected, but on the HMI, a fake data was shown to ensure that the operator is not known of this incident. And because of this, there was an failure in the ICS operations. What is the significance of this attack? The first known malware designed to physically damage industrial equipment, demonstrating the potential for cyber weapons to inflict real world harm. Triton 2017 attacked safety instrumented systems. So, at a Saudi Arabian petrochemical plant, the safety systems were attacked. The attacker gained access to a safety controller, example Schneider, via the plant's network, attempted to disable safety features intended to prevent dangerous accidents. When working with field devices and human lives, there are some devices that are responsible to ensure that people do not get hurt, and attackers often try to misuse these devices so that there is loss of life and also disruption in the processes. So the same happened here, but this attack could not be completed because there was a malfunction in the malware's code that prevented the disaster. It was the first known malware to directly attack the ICS systems, escalating the risk from process distribution to potential loss of life and an environmental disaster. Now, in the 2021 Colonial Pipeline ransomware attack. So, Colonial Pipeline was an organization and a major organization in the United States. So, what happened? Dark side groups on the IT systems installed the ransomware, prompting the company to proactively shut down the pipeline operations. This disrupted the fuel supply on the East Coast for nearly a week, causing shortages and public panic. Significance: highly attacks on the IT networks of ICS operators can still have immediate consequences for OT processes. So basically, the IT network can lead to an attack on the OT network. So this is of significance on this attack. And now the latest attack that happened on on ICS infrastructure was Frosty Group. Frosty Group attack was on a Ukrainian energy infrastructure where an attacker through MySQL databases and then using Modbus gain access to the critical devices. Modbus is an ICS framework which is used to communicate to the field devices. The framework is often unencrypted, which can lead to unauthorized access to critical infrastructure. Now, let's see what would be the consequence of these breaches. For example, try to imagine this from a point of view that you are inside the plant and a breach happens. Then what would you do? Operational disruptions. Of course, my plant stops. In case of a breach, the attacker can easily stop the plant, causing financial loss, service outages, and extended downtime. Breaches can often stop industrial processes, abruptly halting manufacturing lines, energy production, or supply operations. Compromise ICS in utilities can lead to water contamination, blackouts, or disrupt public transportation system. So basically, it will be an easy for an attacker to get into this ICS environment and just stop everything. So that is why the security is very critical here. Safety hazards, physical harm, attacks targeting automation logic, like altering set points or disabling safety systems, may cause equipment failure, explosion, or hazardous chemical releases, endangering workers and the public. Loss of safety mechanism. Malwares like Triton targeted safely instrumented systems, attempted to disable automatic proactive shutdowns designed to prevent catastrophes. Further, as you know, I already highlighted that when working with field devices and people, there is risk of safety, which in case a malware is attacks the safety devices, there will be a loss of life. Let's talk about environmental damage. Manipulation of the processes can lead to overflow or spills or release of dangerous substances in the air, soil, or water bodies, causing a harm to the environment. And with the harm to the environment, the harm will eventually come to the people. Some breaches result in persistent environmental harm involving costly remediation and regulatory fines. Now, it is obvious that if my plant stops working, there would be some economic losses. Direct financial losses will occur when the plant directly stops functioning and all your systems come to a halt. Stopped production and infrastructure damage lead to a loss of revenue, repair costs, and potential compensation to affected customers. Affected plants or utilities can interrupt supply chains, causing downstream losses for multiple industries. And if you combine all the above factors, you can now easily guess how it will impact national security. Let me give an example. For example, a power plant stops functioning. It will affect the transport, it will affect the telecommunication, and will easily cause a nationwide panic attack. So this is why ICS breaches are very critical, and we have to immediately give attention how to secure these ICS breaches. So now let's move on to that. What are the ICS security architecture essentials? So here comes the really interesting part. Now we know how to attack them. Let's see how to stop them. So network separations. So we have to isolate the ICS network from the corporate IT network. Now let me recall you from the previous slide. On the layer floor, enterprise network different from the control network. Firewalls and DMZs. Implementation of robust firewalls and a demilitarized zone. But remember, with proper configurations according to security best practices. Limited access. Block direct internet access. Limit connections to a secure gate. So now, we don't want anyone to access the ICS, but there will be people who will be responsible for maintaining the infrastructure. For them, we can enable a secure gateway and prevent malicious actors to accessing the network. We can also implement role-based access control so that we know that only authorized persons are accessing the network. Now let's deep dive into each of these after I have this overview. Network segmentation in the ICS. Our ICS networks using strict segmentation to enforce the principle of least privilege to the network layer. So here we are saying that there should be zones inside the ICS to reduce the attack surface, and the principle of least privilege should be followed. Separate enterprise IT, DMZ, supervisory control, and field networks with multi-layered firewalls with security best practices configuration that enforce stateful inspection and deep packet inspection. DMZ. Use the DMZ for securely aggregating ICS data and provided controlled access to the enterprise network. Incorporate application layer gateways to sanitize data and deploy one-way data diodes. So now it will ensure that there is no malicious commands entering my device, but all the necessary information is flowing out of my device, where the unidirectional flow is required for high security. Zero trust principle. We have to adopt the principle of zero trust by authenticating and authorizing every connection, even within ICS zone. We can leverage mutual TLS, certificate validation, and segmentation to minimize trust assumptions. Let's see what's next. Authentication and access controls. Now, as I've already highlighted, that if a person get access to an ICS network, there would be a huge loss, not only as a financial risk, but environmental risk also to the nation. So authentication and access controls plays a very important part. So for that, what can we do? A centralized authentication system. We can employ Windows Active Directory, for example, to ensure that there are proper group policies that are in place for user authentication, proper password policies, proper account logout policies, central management of devices, users, and services. This will ensure that there is no user that can be compromised easily. If we implement proper policies, we will ensure that the attacker can not easily gain access and the users are following the security best practices. Role-based access control. We have to define the roles of each user and how much access we have to provide. The role-based access control ensures that each user is provided with a role that is important for him or her. The principle of least privilege is to be followed here because we don't need to create an overprivileged user which, if compromised, can access the whole plant. Remove defaults. So we have to, of course, eliminate all the default credentials. Default credentials increases the risk of direct access by an adversary. So eliminating all the default credentials will easily ensure that there is no attack using a default credential. Monitor access. So monitoring plays an important part in ICS environments. We have to monitor every network, every packet, and every application to ensure that all the audits and access events are genuine. We don't want any unauthorized audit or access events. Let's talk about a little about risk management for ICS. So what we can do? Classify the ICS systems as per FIPS and NIST standards for confidentiality, integrity, and availability. But in the case of ICS, the availability takes precedence, emphasizing operational impact for availability and integrity. Selection of security controls. Map security controls from the standards tailored for ICS environments, especially for SCADA and industrial protocols, including legacy devices, physical security, network protection, and anomaly detection also. Control implementation. Conduct penetration testing using ICS specific framework like 62443 specific vulnerability scanners to validate security controls. Continuous authorization and monitoring. Implement automated compliance monitoring tools for real-time visibility and intrusion detection. Patch management workflows to be adopted for ICS. maintain proper documentation detailing all security controls, exit criteria, and incident response plans. So this is some things that I would like to highlight for risk management in the ICS environment. Now, legacy system, legacy system, legacy system. Throughout the webinar, I have highlighted what are legacy systems, and now we take a deep dive into the challenges and how we can solve those challenges. First, no native security features. Legacy systems such as old server versions or an old PLC do not have any native security features because the security patches are not available anymore. So they are vulnerable to latest security threats, unsupported OS or protocols, which is of course a threat that we have to solve. The OS is old, the protocols are old. We cannot implement new protocols because for that we have to upgrade the system, we have to stop the plant. That is not happening. So what will be our approaches? We have to play a little smart here. What we have to do? We have to implement firewalls and IDS. Firewalls to ensure that there are proper network segmentation as per security best practices. IDS, intrusion detection system, so that we can monitor every action, the flow of network, and every login attempt on those systems to ensure that there are no malicious or unauthorized activities in place. We can also do virtual patching. Now, what is virtual patching? We can detect if there are any malicious functions or malicious commands that are being sent to the system. Malicious commands may affect the system. So we can catch those commands on the network level to ensure that the vulnerabilities on those systems cannot be exploited. Proper network isolation, as I have said, using DMZs and proper configuration on network devices such as on switches, routers, firewalls, gateways, we can ensure that proper network isolation is there. Continuous monitoring and visibility. Now, monitoring plays an important role in any kind of infrastructure. Here, we can employ IDS system to deploy ICS intrusion detection in the network to ensure that the ICS devices stay safe for any kind of malicious functions or malicious access attempts. SIEM integration. We can integrate logs with security information and event platforms to ensure that logging and monitoring as per security best practices are in place and easily identification of any kind of malicious attack can be done. Anomaly detection, monitoring unusual behavior, network traffic anomalies, and remote access events, which are important in case of ICS environments to ensure that no unauthorized adversary can gain access is important. So now, at the end, I would like to highlight on what are the best practices in the ICS cybersecurity. Regular risk assessment. It is ensure that regular risk assessment to be done on plant level because risk assessment ensures from an internal and external point of view that what are the vulnerabilities or what are the misconfigurations that can be exploited by an attacker. Least privilege access. We can follow the principle of least privilege to ensure that there is no unauthorized or overly permissive system or service inside the environment. Firewalls and network segmentation is of course something that I have highlighted during this webinar a lot. Disabling unused ports and services. So we have to reduce the attack surface and to a minimum. For that, we will only ensure that the ports and services required for the functioning of the architecture are only enabled. Tabletop incident response exercises. We have to regularly conduct trainings and exercises of the engineers and operators in the infrastructure so that they are aware of the latest security preventive controls that they have to take or the detection of events that they have to take to ensure that the architecture is safe. Vendor and supply chain vetting. The attacks are not often from the inside. They can also come from a third party vendor. For example, a third party remote access software. We have to ensure that the vendor and supply chain management is proper. We can also create a software bill of materials to ensure that the applications, libraries are in check. A vulnerability management system will also help. So now I would open up the session for some questions. So now you can fire away your questions and some suggestions that you would like to ask me.
Thank you so much for that insightful and engaging presentation. We've covered a lot of valuable information today, and I'm sure everyone has gained a lot from today's presentation. If anyone has any query, please let us know. We are waiting in the chat box.
So I see a question related to the attack on Iran. So it, as I have previously told in the slides, the attack that happened on Iran was Stuxnet. It happened in 2010. So basically, a highly sophisticated worm. What is a worm? A worm is something that spreads through files, USBs, disks, drives. So basically, a malicious USB drive that might have been plugged in somewhere else and carried a worm got inside the plant and and that targeting the Siemens PLCs. So it basically manipulated the HMIs to show false data, and on the other end, it manipulated the field devices. As you know, the field devices are the major components of ICS infrastructure. Manipulating the field devices and preventing the controller or the operators to detect unusual activity led to the downfall of security infrastructure there. The significance of this is that it's the first known malware designed to physically damage industrial equipment and demonstrating cyber weapons to inflict real world harm. How do we ensure OT plants are secured enough when they have legacy system? So what we can do in this case? Legacy system, as I told you before, proper network segmentation using firewalls with security best practices configurations. We can also enable IDS SIEM solutions to ensure that there are proper monitoring of the network and basically employ proper segmentation and a DMZ between the enterprise layer and the OT layer, and also prevent unauthorized remote access to the legacy systems. Deploying and running ICS networks on private network and strictly isolated from internet. Yes, there are often infrastructure that are not connected to the internet, and there is a functioning ICS environments. That is what is recommended. But we have to also say that the ICS networks often require maintenance. For that, we may require some remote support. So we can easily set up secure IPsec tunnels using VPN, using firewalls, or any other secure remote access way. Do not use any third-party remote access software that would increase the attack surface and enable the attacker to gain access. But yes, an internal demilitarized ICS network is good. So again, about the legacy system, what are the most effective methods to implement network segmentation in ICS environments? To implement proper network segmentation, you can use network devices such as firewalls, switches, routers. So industrial firewalls, industrial switches often have controls and policies to implement proper network segmentation. You can also use data diodes to ensure that there is only flow of one-way traffic. So these are some principles that you can use to perform proper network segmentation. Any further questions? Might want to ask anything regarding something that I have said in this, or you have to understand some kind of devices or infrastructure related to ICS networks or any kind of security implementation, now is the time to ask. Machine learning and AI. What role do machine learning AI tools play based on modern OT threat detection? So basically, what if I take a real world example or real world implementation? What we can do is we can implement a SIEM solution to gather all the data or a network based intrusion detection. So basically gather all the data regarding the network or any kind of intrusion, and then we can pass it through an AI to analyze and basically be ready and take a preemptive response. For example, if I see that some default credentials are being used to access the devices, an AI can easily generate a list of credentials and we can prevent them from being used in our plants. So this is just a small example how AI can be used. But implementing complex AI machines and machine learning in ICS infrastructure where the network bandwidth is low and where we need real-time response, it's a little bit difficult. Also, we can use behavior analytics to understand and reduce false positive alerts from security mechanisms such as antiviruses. Seeing scope of centralized ICS with increasing penetration of network upgradation 5G, 6G, 10G. Okay, a very nice question. So as we are moving towards the next generation of technology, the Web 4.0, we can all add IIoT, intelligent Internet of Things. We can see that the flow is being controlled by devices like data diode, where the flow to the ISS device is only one way. We can only get data from the devices. There is no data or malicious things that can be sent to the devices. Also, we can use secure remote access methods to access the environment. And however, the integration of more endpoints and third-party services, especially with 6G's decentralized nature, increases the exposure to potential threats or different kinds of attacks, making centralized ICS both a target and a critical node for data defense management. I think not. So when the question comes, it is safe or not? I think it is a bit risky. Basically, when you talk about the hardware equipment is provided by the OEM after secure testing and before implementing into the environment You can do a secure configuration review as per security best practices, or a simulation of a penetration test or a vulnerability assessment, so that you know that, okay, these controls are improper, these are the default credentials being used, these are the misconfigurations. You can identify those and then apply them to ensure a safe hardware inside your OD systems.
Thank you once again, everyone, for joining us today. We appreciate your time and participation. Have a great day, and keep joining us for these wonderful sessions and having this kind of insight. Thank you and have a wonderful day ahead.